Hi Kathy, good evening. Good evening, Ma.
Good evening, sir.
Okay. Have you gone through the solutions? Have you read solutions concept?
What, sir?
You read the solutions chapter
Yes, sir, I did.
to whatever we completed. You read or not?
Yes, sir.
Okay. So today we are going to discuss about the colligative properties, Ma. Okay. So let them join here slowly, one by one. They're going to be joined. So I don't want to waste our time. Okay. So because of I'm getting only 15 minutes time. In that also, so somebody there logging very lately. Okay, then I can start again. So colligative properties. Colligative properties. Colligative property. Now, what is mean by the colligative properties? So what is mean by the colligative properties? So colligative properties is nothing but here. So here, pure solvent it is there. So pure solvent is having its own properties now. Similarly, solute also it is having similar properties. Okay, pure solute, pure solvents are they having their own properties. Sir, what is the simple, what is the best example for that one means here? For example, if you take sugar, what is the physical state of the sugar? Sugar can be exist in a solid form and it is exist in a crystals form only. Is it right, Kathy? Okay,
Yes,
sugars
sir.
sugars are present in a crystalline formation and solvent we are taking as a water. Okay, so water is liquid form, but when you dissolve the sugar in a water, when you dissolve in a sugar in a water means it gives as a uniform solution. Okay, it gives as a uniform solution. So before dissolving the sugar, what is the taste of the water? Water is having any taste?
No, sir.
So because of it is a tasteless, okay, and odorless, colorless also. But whenever you add sugar in the water, so water it becomes as a sweet in taste. That means the properties of the solution is changed or not after adding the solute.
Yes, sir.
Okay, so according to that one, so when the non-volatile solute is dissolved in a solvent, the properties of the solution is going to be changed. That properties only we can call as a colligative properties. So what is the colligative properties means here? So when the non-volatile solute is added to the solvent, the properties of the solution is going to be changed. That properties only we can call as a colligative properties. Okay, so colligative properties are depends upon the nature of the solute. Okay, the properties are depends upon properties are properties are depends upon nature of solute. Okay, sorry, depends upon the number of solute molecules. Properties are depends upon the number of solute molecules. Number of solute molecules irrespective of their nature. Irrespective of their nature. Their nature. So that means colligative properties are independent on the nature. That depends upon the number of solute particles only. Okay, so according to that one, what we can say means here The colligative properties are depends upon here number of solute molecules or solute particles in the solution irrespective of their nature. Okay, sir, what are the examples of the colligative properties? Means we have a 4 types of the colligative properties. How many types of the colligative properties are there? 4 types of the colligative properties are there. So this concept is very, very important for the JEE and NEET level examination. Okay, sir, what are the 4 different colligative properties we are having? Means one is relative lowering vapor pressure. Relative lowering vapor pressure. Relative lowering vapor pressure. Relative lowering vapor pressure. Second one is elevation of boiling point temperature. Elevation of boiling point temperature. Elevation of boiling point temperature. Boiling point temperature. Okay. And so third one is depression of freezing point temperature. Depression of freezing point temperature. Depression of freezing point temperature. And fourth one is osmotic pressure. Fourth one is osmotic pressure. Osmotic pressure. Okay, so what are the examples means here? So we have what are the colligative properties means? So we have a 4 different types of the colligative properties. What are the 4 different types of the colligative properties we are having means here? So one is relative lowering vapor pressure. Okay, second one is elevation of boiling point temperature. Third one is depression in freezing point temperature. Fourth one ma osmotic pressure. So what is the fourth one means here? So fourth one is nothing but here osmotic pressure. Okay, so all these are the colligative properties. In this one colligative property is depends upon the another colligative property. Okay, in this one colligative property is depends upon another colligative property. If you know the one colligative property means by using that one we can calculate the another colligative property also. Got the clarity? So all of you got it here. So what I mean the colligative properties? Samhita, Sirisha, Aditi. Okay. Okay, all. Sir, how many types of the colligative properties are there? How many types of the colligative properties are there, ma?
4, sir.
Okay. So these colligative properties are depends upon the number of solute particles or nature of the solute particles.
Number of solute particles.
Okay, number of solute particles. Colligative properties are depends upon here number of solute particles. They are independent on nature of the solute particle. Okay, so one colligative properties depends upon the another colligative property. So in that one, first one we can see ma. So what is the first one means here? Relative lowering vapor pressure. Relative lowering vapor pressure. Vapor pressure. Simply in short form, this we can write as a RLVP. Okay, so what is the short form means here? RLVP. Okay, sir, what is meant by the relative lowering vapor pressure? Okay, so same concept also in some books what they had given na. So relative lowering vapor pressure is going to be explained by here. So Raoult's law. According to the Raoult's law, the partial pressure of the solution is equal to, it is the product of vapor pressure of the pure solvent and mole fraction of the component or mole fraction of the solute or solvent is called as a vapor pressure. So two conditions are there. When the solution is containing non-volatile solute, we have one formula. When the solution is containing volatile solute and volatile solvent, mean that time we are having some formula. Okay, but that concept also they explained based on this one only. Okay, so here also relative lowering vapor pressure. So before going to the relative lowering vapor pressure, first we have to discuss about What is mean by the lowering vapor pressure? What is mean by lowering vapor pressure? What is mean by the lowering vapor pressure? What is mean by the lowering vapor pressure? Okay, for example, first my question is my here. So here, pure solvent it is there. Pure solvent. For example, you had taken as a water. Water is having the high vapor pressure or not? By heating at 100 degrees centigrade, it has a high vapor pressure. Whatever the vapor pressure is that we are considering it is as a P naught. Okay, so that we can consider it as a P naught. Whenever you add non-volatile solute to the solvent, okay, whenever you are adding non-volatile solute to the solvent, the vapor pressure is going to be decreases or increases? Decreases or increases, ma? In a solution, first we had taken as a pure solvent. If you take any solution, pure solvents are having high vapor pressure. Okay, so that vapor pressure can be represented with the P naught. For that solvent only, whenever you are adding the non-volatile solute, the vapor pressure is going to be decreased. Then the vapor pressure of the solution, vapor pressure of the solution, vapor pressure of solution can be represented with PS. How we are going to represent, ma? So vapor pressure of the solution can be represented with PS. So if you compare these two, pure solvent, vapor pressure of the pure solvent, vapor pressure of pure solvent and vapor pressure of the solution. So which one is having the greater the value? Which one is having the greater the value, ma? Whether pure solvent or solution?
Pure solvency.
Pure solvent, ma. Okay, so 1 second, ma. Right, ma. So in this one, vapor pressure of the pure solvent is P naught and vapor pressure of the solution is PS. So in this one, which one is having the greater the value means here, pure solvent is having the greater the pressure while comparing with the solution. Okay. Now, let us see. Lowering vapor pressure. Sir, what is the lowering vapor pressure means here? It is the difference between the vapor pressure of the pure solvent and vapor pressure of the solution is called as a lowering vapor pressure. Okay. So what is the lowering vapor pressure means here? So lowering vapor pressure is nothing but lowering vapor pressure. Sir, where lowering vapor pressure is nothing but it is the difference between vapor pressure of the pure solvent and vapor pressure of the solution is called as a lowering vapor pressure. So lowering vapor pressure also can be represented with the delta P. So how we are going to represent the lowering vapor pressure, ma? Lowering vapor pressure can be represented with here delta P. Hence delta P is equal to P naught minus PS. Okay. This equation we can derive from, okay, so we can derive from the Raoult's law. Okay, so same equation we can derive from the Raoult's law. Sir, what is the Raoult's law? Vapor pressure of the pure solvent. Okay, vapor pressure of the solution according to the Raoult's law. Okay, according to the Raoult's law. According to the Raoult's law. According to the Raoult's law. So how we can write this here? So total pressure is equal to, so pure solvent into mole fraction of the component. Okay. If we take non-volatile solute mean that we can write as here. So P naught into XP. Okay. So total pressure of the solution. Here total pressure of the solution is we are taking as a lowering vapor pressure only now. So hence in place of this one, we can write as a delta P. Hence delta P is equal to P naught minus P naught into XB. Okay, so PS wavering pressure of the solution we can write as a P naught into XP. What is another formula we are having according to the Raoult's law? According to the Raoult's law, what is the formula we are having? What is another formula we are having? Two formulas are there. Do you have any idea or not? I think so. No one they're having the idea. Is it right? Okay, actually two formulas are there. What is another formula means here? Whenever it is volatile solute, okay, or volatile solvent also means here, if the vapor pressure of the solution is directly proportional to or is equal to product of vapor pressure of the pure component and mole fraction of the component, mole fraction of the solvent also we can write. Because of whenever in non-volatile solutes, we can write as, now I got the clarity. Okay, so in non-volatile solutes, the vapor pressure of the solution is depends upon the mole fraction of the solvent only. According to that one, the pressure is equal to, we can write as a P naught into XA. Okay, so P naught into XA we can write. Now, here we can write as a lowering vapor pressure. Lowering vapor pressure we are representing as a delta P is equal to P naught minus PS. As per the Raoult's law, what is the PS value? So PS value is nothing but P naught minus P naught into XA. P naught into XA. In this one, what is the common thing it is there? So what is the common thing it is there, ma? P naught value only, na? Hence, P naught if you take common means, you can write as a 1 minus XA. So we got as a 1 minus XA. Where we got as a 1 minus XA, ma? Where you got 1 minus XA?
XB, sir.
Mole fraction. According to the mole fraction. So XA plus XB is equal to 1. Then if XB is equal to 1 minus XA only, XA only, na? So that means in place of 1 minus XA, we can write as a XB or not? We can write as here XB. So according to that one, delta P is equal to P naught into XB we can write. Okay. So in this one, what is the delta P? Delta P is nothing but lowering vapor pressure. Sir, how we can write the lowering vapor pressure? P naught minus PS is equal to P naught into XB. Okay. So now this equation, if we simplify means how we can write ma? So this equation also we can write as here P naught minus PS divided by, here P naught it is there. If the P naught, if you take this side means you'll get as here P naught is equal to XB. Okay. Sir, in this one, relative lowering vapor pressure. Sir, what is meant by the relative lowering vapor pressure means? It is the ratio of lowering vapor pressure and vapor pressure of the pure solvent is equal to mole fraction of the solute is called as a relative lowering vapor pressure. Got it all of you? What is meant by the relative lowering vapor pressure, ma? Relative lowering vapor pressure is nothing but it is the ratio of lowering vapor pressure and vapor pressure of the pure solvent is equal to mole fraction of the solute. Mole fraction of the solute is called as a relative lowering vapor pressure. Okay. In this one, you're writing as a XP. How we can define the XP? What is meant by the XP? XP is equal to mole fraction of XP is equal to mole fraction of solute. Okay, so how we can write the mole fraction of the solute? XP is equal to, what is the formula we can write? What's the formula we can write, ma? How we can write the formula for the mole fraction of the solute? Any one of you? How we can write the mole fraction of the solute, ma? NB by Na plus NB. Forgot the formula, sir. All of you? Huh? All of you forgot the formulas? Aditi, Samnita. How we can define the mole fraction of the solute? Mole fraction of the solute is equal to NB by Na plus NB. What is going to be the mole fraction? How we can give the definition for the mole fraction? Aditi, what is the definition for the mole fraction?
So number of moles of solute divided by number of moles of solution.
Number of moles of solution. Okay, or that is also we can define as a number of moles of one component by the total number of components, total number of moles of components present in a solution also we can write. Okay, next one more question. Is mole fraction is depends upon the temperature or independent on the temperature? Kathy, Samhita, Sirisha, is mole fraction is depends upon the temperature or independent on the temperature?
Sir, I think it's independent of temperature.
So mole fraction is independent on the temperature. Samhita, so why it is independent on temperature? Ma, can you give me any reason? Is there any reason why the mole fraction is independent on the temperature? Any one of you? Sai, Akshit? Samhita, your voice is striking, ma. Others, why the mole
What's it?
fraction? Your voice is striking, ma. I didn't hear your voice. So why the mole fraction is independent
Sir,
on
I
the
don't have good.
Aditi?
Yes, sir.
Why the mole fraction is independent on the temperature?
Because number of mole depends on mass and not volume or anything, and mass is not temperature dependent.
Very good, Aditi. Okay, so actually number of moles are depends upon the mass. Number of moles we are going to be calculated by the given mass by molar mass. So we are not taking any volume in this one. Okay, if it is volume means then it is depends upon the temperature here. So mole fraction and molality both are independent on the temperature. Okay, Sirisha, so which are depends upon the temperature? Which concentration terms are depends upon the temperature? Sirisha, which concentration terms are depends upon the temperature? Which concentration terms are depends upon the temperature? Make it fast, ma. Which concentration terms are depends upon the temperature? Sir, molarity and normality or depends upon the temperature. Molarity and normality or depends upon the temperature. Okay, so according to the Charles law, because of the volume it is that the volume is directly proportional to the temperature according to the Charles law. That's why molarity and normality all depends upon the temperature. Now, if you substitute the XB value, sir, so what is the XB value got as here? So P naught minus, so PS by, so P naught is equal to NB by Na plus NB. Okay, so we have a one concept. What is the concept we are having means here? Raoult's law is applicable for dilute solutions or concentrated solutions. Raoult's law is applicable for dilute solutions or concentrated solutions.
Sir, isn't it applicable for both?
No, ma. Okay, so actually most probably we are considering it as a dilute solutions only. Okay, so clearly I had given the statement here. So Raoult's law is applicable for dilute solution. Okay, and that is also solution. It has to contain the non-volatile solute.
Sir, why is it
Solution it
like
has to
that,
contain.
sir?
Ma?
Why is it applicable to only?
So because of concentrated solutions means if the number of solute particles are increases, Okay, vapor pressure is completely going to be decreases only, ma. I told that vaporization depends upon the vaporization, and that is also you are adding non-volatile solute. Non-volatile solute means solvent molecules are replaced by the solute. If the solvent molecules are replaced by the solute means surface area is going to be decreases. If the surface area is decreases means vaporization is going to be decreases. If the vaporization is decreases means automatically vapor pressure also is going to be decreases na, Samhita?
Yes, sir.
Okay, so that's why this concept mainly he has taken for dilute solution and which contains the non-volatile solute. Okay, but if you take volatile solution means vapor pressure is going to be increases. Both the solute and solvent are they converted into the vapors and they causes the more pressure. Okay, right, man. So that's why for dilute solutions, for dilute solution. But dilute solutions means solute content it will be less or more, which we can call as a dilute solutions. The solutions which contains the less amount of the solute only we can call as a dilute solutions only na. So for dilute solution in denominator part, in denominator, okay. So I think so some spelling mistake is there means try to understand my here. Okay. So some denominator, my NB value is negligible. NB is less than 1. So less than 1 means here it is negligible. If it is negligible means how we can write the formula? So P naught minus, so PS by, so P naught is equal to NB by NA. Okay, in this one NB we are writing. NB we are writing. So what is meant by the NB? NB is nothing but number of moles of the solute. How we can calculate the number of moles of the solute? How we can calculate the number of moles of solute, ma? How we can calculate the number of moles of solute? Any one of you. So number of moles is given weight by molar mass here. So this we can write as a weight of the solute by molar mass, molecular weight of the solute. And Na how we can write formula? So W by WA by, so weight of the solvent by, so molecular weight of the solvent, molecular weight of the solvent. If you substitute these two formulas in the above equation, so what you will get as here? So P naught minus, so PS by, so P naught is equal to, so we can write as a WB by MB. So directly I'm writing the formula into. So because of denominator, it comes to the numerator. That means MA by WA. Okay. So this is the final formula we are using to calculate the molecular mass of the solute. By using this formula, we are going to calculate the molecular mass of the solute. So relative lowering vapor pressures, colligative properties can be used to calculate the molar mass of the substances. Clear? Still anyone having doubt until here? Okay. Shall we do one numerical based on this one? Samita?
Yes, sir.
Okay, so we can do one numerical, ma. So you can note down the question. You can note down the question. Different questions only. If you are having any NCRT textbook or something, ma? So one
Sir,
second.
can you repeat your question?
So one second, I didn't give the question. Okay, just I'm searching for the question only. Okay. Now I'm getting the questions. Okay, right. Here they had given one question here. Okay, so what is the question they had given means here? Vapor pressure of water at 23 degrees centigrade. Can I write the question? Right. Just be hold and I'll give one question here. Okay, 1 second, I'll give the question. Directly I'll paste the question. I think so you can't see here. Until that, just go through this concept here, just to revise the concept. What is the formula we are using in it all? Okay. My solution chapter is finished in your schools for everyone. Is the solutions concept is finished or not? All of you.
Yes, sir.
Now it is revision, then it is for you. Ready to solve the question. Then can I forward some questions to you? Didn't find any exemplar questions also here. Okay. Here one question is there, but let us see. Anyway, you try this question. Anyway, I'll give this question here. The vapor pressure of water at 23 degrees centigrade is. I'm writing the question. One check it out. The vapor pressure of the vapor pressure of water at 23 degrees Celsius is 19.8 mm. 0.1 mole of glucose is dissolved. 0.1 mole glucose is dissolved. 1 mole of glucose is dissolved in 178.2 grams of the water. 2 grams of water. So what is the vapor pressure of resultant solution? What is the vapor pressure of the resultant solution? What is the vapor pressure of resultant solution? So I can give the options also. So what are the options they had given means here? Option C, option A is 19.0. Option B is they had given us a 19.6, 19.602. Option C is 19.402. Option D is 19.202. So what is the answer? What is the answer, ma? Any one of you? What is the answer? Any guess? So what is the question they're asking? All of you copied the question. The vapor pressure of the water at 23 degrees Celsius is 19.8 mm. 0.1 mole glucose is dissolved in 178.2 grams of the water. So what is the vapor pressure of the resultant solution? That is the question. And I give options also. What are the options we are having means A is having 19, B is 19.602, C is 19.402, and D is 19.202. Any one of you? So what is the formula we can use? First of all, the question is related to relative lowering vapor pressure only. Na? If the relative lowering vapor pressure means what is the formula we can use? We can use as a two formulas. So P naught minus PS by. So P naught is equal to NB by NA plus NB. If you see in this question means they had given us a P naught value. So P naught value, how much they had given? 19.8. So they're asking to calculate the PS value and NB value. NB value is equal to how many moles they had given? 0.1. Then what about the Na value? Is they had given Na value, ma? All these are this kind of questions only. It is there in JEE calculations only. Numerical questions it will be there based on this chapter. What is the Na? Weight of the water they had given. That means, so how we can calculate the number of moles of the solvent means here given weight by molecular weight. That means 178.2 divided by 18. Okay, if we simplify this one more, we can calculate the number of moles. So how much will get as the number of moles here? Number of moles, ma. I think so 6 threes here. 6 twos, sir. 6 twos means 58. It will be there. 58 means how much will get us here? 58. 58 means here. 6 nines. 56, sir. 178 by 2. 178 by 2. One switch it out, ma. How much you are getting? So 2 6, sir. 2 nines, 2 ones, 2 nines, 69.1 divided by 9. 69.1 divided by. What is the value of 69.1 divided by 9 means? How much you will get, ma? Six point. 6.1 number of moles is equal roughly if you take means 6.1 is the value. If you substitute all these values, ma, all of you having next class, you do one thing. So all of you solve this question and you can come here. We will discuss in the next class. Okay?
Yes, sir.